Hello everyone. So in this video tutorial, we'll see the layout of CMOS inverter. So in the previous video lecture tutorial, we have seen how the schematic of CMOS inverter, and we have simulated the DC analysis and transient analysis. So here we will draw the layout for this schematic. So to draw the layout for the schematic, first thing what we have to do is we have to create one more cell in the same library, that is CMOS lab 1. Okay, so to create cell, we have to go to cell option and we have to select new cell. So we can see the library name, so it has to be in the same library. Okay, that is CMOS lab 1. So we can see it is available. We can see from here this the library name is CMOS lab 1, and whatever the schematic name we are given, we have to give the same name for the layout. So what we are given for schematic inverter, right? So we have to give the same name for the layout. Okay, so give the same name, that is inverter, and instead of schematic, now we have to select layout. Instead of schematic, we have to select layout and click OK. So when I click OK, you can see that the inverter, okay, you can see that the two cells are now combined together, and those are in the library, that is inverter. So we can see we will have a circle with three colors, that is blue, red and yellow. So we should get this circle with three colors, blue, red and yellow. Okay, so we have to make sure that we have to give the same name what we have given to inverter. So we have given inverter for the schematic, so same name we have to give for the layout. Okay, so here red color is for schematic and yellow is for layout. Okay, then so that is with respect to the creation of cell for layout. Then now we have to draw the layers for CMOS inverter. Okay, so in the components, now I can see the components are now changed. Now those components are not in the form of symbols. We have in the form of layers. Okay, we have in the form of layers. And for layout, don't use grid lines. Okay, for layout, don't use grid lines. Keep it blank. So to take it off, so if you don't want to make use of grid lines, press again Ctrl G. So you will get a blank print like this. Okay, if you want again the grid lines, you can press Ctrl G. If you don't want, you can again you press Ctrl G. Okay, on and off, we have to make use of the same key. It is a Ctrl G. Okay, press Ctrl G, you will get the green lines, and if you press again Ctrl G, you'll get a blank window like this. Okay, then first the first layer I will use here is PMOS, because the first transistor is what PMOS transistor. I will make use of PMOS transistor, which is at the bottom. You can see it at the bottom. We have the PMOS transistor. I will select that and I will keep it in this form like this. I'll keep it here like this. Okay, so this is my PMOS transistor. Okay, if you want to rotate, means the pink color, that is the pink color here, it is horizontal, and the green color it is vertical. If you want to rotate, you can press Control J for Control J to rotate the layer. Okay, so I will select this and I will press Control J. Okay, see this, you can see Control J. Select this, Control J, it will rotate. Again, if I press like this, fine. So this is the first layer we have taken. Okay, we have taken the first layer. Then we have to change the width. So whatever the width we have given in case of schematic, the same width we have to give for in the layout also. Okay, in the layout too, we have to give the same width what we have given the schematic. So whatever we are giving the values in the schematics, the same thing, the same values we have to give in the layout. Keep in mind. Okay, so we have given the width for PMOS as 20. So I will so to change this, so I will double click on this PMOS transistor. Then you can see the width. So the width of this node properties, the width I will change to 20. Then length by default 2, like this. Okay, you will get a window like this. Okay, I will get the after changing the width of PMOS transistor, you'll get a PMOS layer in this form. Okay, then so we have to give the name. So what we have given the name for PMOS transistor in case of schematic. Similarly, we have to give the name for this in case of layout also. So select this PMOS transistor, go to tools, again the same procedure, go to tools, simulation spice, and select set spice model. Okay, select set spice model. So the text is not so the text is not visible here, the spice model. So you can zoom in, so you can see, zoom in. So now I want to select this, I want to select this spice code. So if I click on this, it will not, it will not be selected, it will not be selected. Then what we have to do, press control, hold the control key, and if you move the cursor, if you move the cursor across the text, that is spice model, then if I select now, it will get selected. Okay, it will get selected, it will get a red cross mark like this. Okay, so when it becomes a red cross mark, press control I, press control I. Okay, so what I said, so first thing, so we have to set, give the name for this CMOS inverter, that is PMOS inverter. Select the PMOS inverter, go to tools, simulation spice, set spice model. Then if you want to select this text, if I go and select, okay, the spice model, it will not be selected. So we have to we have to hold the control key, and select the spice model text. So when I press control key, when I hold the control key and if I select, it will get selected. So when it gets selected like this across red mark, press control I and change the name to PMOS. So you can see PMOS will appear here on the PMOS transistor like this. Okay, so now it is zoom in. Okay, it is in the form of zoom in. Then to fit to the to fit to the window, to the fit to the window, go to window and click on fill the window. Okay, click on fill the window. Okay, like this, it will get fitted. So we can zoom out. Okay, control 0, right? Then we can move the layer wherever we want, and make sure that you press control press F5, press F5. Okay, press F5, or you can go to tool window tools, DRC and F5. Okay, so you can press F5, you can see no errors are found at the bottom. Okay, okay, you can see at the bottom, that is electric messages window. You can see no errors are found. Okay, whatever we have drawn till now, it is correct. Okay, so what we have to do to find if any errors are there, go to tools, DRC, check hierarchically, that is F5. The shortcut key is F5. DRC stands for design rule check. DRC stands for design rule check. Okay, so this is PMOS is created. Okay, now we have created the PMOS transistor. So we have changed the width to 20 and we have given the name as PMOS transistor. Okay, then to make the contacts in layout, we have to make use of enact. Okay, we have to make use of what? Sorry, p-act. Okay, if you have to make use of p-act here. Okay, if you have to make use of p-act like this, so we have to make use of this p-act because we have to make the connections. So here, if I zoom in and if I show what this layer is, this pink color, the pink color is what? The pink color is the polysilicon or the gate terminal it is. Okay, it is a gate terminal, and whatever the green is there, the green is there, so that is nothing but diffusion. That is nothing but what? Diffusion. Because to form a transistor, okay, into form a transistor, diffusion should cross the n type or p type diffusion. So if you want to form PMOS transistor, the polysilicon should cross P diffusion. If you want to form NMOS transistor, the polysilicon should cross NMOS and N diffusion. Okay, so to form PMOS transistor, the polysilicon should cross P diffusion. To form NMOS transistor, the polysilicon should cross N diffusion. Okay, now here the vertical line, the vertical that is pink color is the polysilicon, and the green color is the P diffusion. Okay, so this is my gate, the vertical gate, and this side it can be drain. On this side it is source. So we have three terminals: source, drain, and gate. Source, drain, and gate. Okay, source, drain, and gate. So we have to make these connections, this P act to the drain as well as to the source. We have to make the connections. Okay, so how to make the connections, we'll see that. Okay, now so we have taken the P act. Okay, we have taken the P act. So you can see here, this layer, the boundary of this P act should match the boundary of this PMOS transistor. Okay, the boundary is what? Here at this point. So this is the boundary, right? So this is the boundary for that is P act. So it should match with the boundary of PMOS transistor. So to match that, so we have to change the vertical size of this P act to 20. So double click on that P act. Okay, double click on that P act, change the Y size. Because we have to increase the Y size, so we have to change that Y size to 20. Okay, so if you see this, so we can adjust this. So now if you see, both both the layers are of the same height, that is y axis is same. Okay, so we have to make use of this layer on the other side also, that is for source. So I will select this, control C to copy it. Okay, control that is copy and paste on the other side. Okay, that is control C for copy and control V for paste. So I will select this, control C, select that control C option, and click on the left hand side and press control V. So if you see this, we will get a rectangular like this. So I place it here. Okay, so I'll make use of arrow keys. I'll make use of arrow keys on the keyboard to make it to move it horizontal, and that is to move it to the left side, move it to the right side, to move it to the top, to move it to the bottom. I'll make use of those keys. Okay, I'll make use of those keys. Now we have both the P act. So I have both P act on both the sides. So I will make the connections. So we have to connect it to the drain, and we have to connect it to the source. So select this, left click, right click, same procedure. Left click, right click, similarly left click, right click, like this. Then so now uh, we have to move this P act layer on the drain. So what we have to do, select this, hold the left key, and move it inside. So when I move it inside, you can see at the top there is a text which is appearing. Okay, that is P act spacing. Okay, the P act spacing at this point it is 12. So if I go on inside, it is decreasing, right? You can see. So we have to make the P act spacing as 3.5. So when it is 3.5, when it is on this diffusion layer, that is 3.5, you stop it like this. Okay, so now see, there is a mismatch here at the boundary, so we can make use of arrow key to make it match. I have take it down, so it will match. Similarly, I will select this, I will select this, and I will hold the left key of the mouse, hold the left key of the mouse, and I will just start moving inside the source, okay, towards the source. I'll start moving towards the source, and if the spacing is 3.5, see, look at the, now it is 7.5. Look, there is small text on that rectangular at the top, that is p spacing is 7.5. So start moving when it become 3.5 spacing, stop it. Now it is 3.5, I will stop it. Okay, so now this is complete, this is a complete PMOS transistor. Okay, this is a complete PMOS transistor. Okay, then you can save it. Okay, save first, control S to save, you can save it, save the library, then press F5 or go to control, go to DRC and select check hierarchically. See, no errors are found. To so till this point we don't have any errors present in the layout. Okay, so after every step you check out, you press control, that is you press F5 and check if we have any errors present in the layout. If we don't have any errors, it is well and good. If we have the errors, we have to rectify those errors. Okay, next, so whatever the procedure we have followed for to create this PMOS transistor, so same thing we have to follow the same procedure to create NMOS transistor. Okay, so whatever the procedure we have followed for this to create this PMOS transistor using the layers, same thing we have to do it for NMOS transistor. Okay, so we have to place it at the bottom, uh, below the PMOS transistor. Okay, so I will select this whole thing. Okay, if you want to move this everything, this PMOS transistor, I will select this everything and just hold the left key and I will move like this. Okay, what I did, if you want to select this everything that is PMOS transistor, then select this PMOS transistor, hold the left key, hold the left key and move wherever you want. Okay, like this. Okay, so I'll keep it here. Then now you take NMOS transistor, follow the same procedure as we did for PMOS transistor. So I will select NMOS transistor, I'll place it here. Okay, now it is in the, see the pink color, it is in the horizontal form. I will rotate it. I will rotate that, press Ctrl J, so it will get rotated. Then now that we have changed the width to 10, because for NMOS we have changed in the schematic to 10, so similarly we have to change it in this layout also. So double click on this. Now you can change the length to 10, change the length to 10, so you can see that. So make sure that you have enough space between NMOS and PMOS transistor. Okay, and also make sure that this NMOS and PMOS are on the same vertical axis. Make sure that those overlap together. See, this overlapping is proper. Look at this. So before that, so make sure that we have enough space between these two transistors. Okay, so we have enough space here. So this much space you keep between the two transistors. So again, we have to give the name for this, right? We have to give for the name for this transistor, that is NMOS transistor. So again, you select this NMOS transistor, select that, go to tools, simulation spice, and select set spice model. Okay, so we have a text will appear on that model. So if you want to see the text, you can zoom in, control 7 to zoom in. And now we have to change this text, that is spice model, to NMOS transistor. So press hold the control key and now you select the spice model. So when it becomes a red cross mark, press control I. Now you change the name to NMOS, like this. Okay, you change the name to NMOS, right? So now we are given the name and we have changed the width of NMOS transistor. Now we have to connect NACT. Okay, so we have to connect the NACT to drain, source and drain. So I'll place it here, I'll place it at NACT here. Then see, again the boundary is not matching it, okay, with NMOS transistor or with of NACT. So we have to change the this x size, that is x size or y size of this connect. So double click on that. Okay, we have to match the vertical axis. So we will change the y size to 10. Okay, I will change the y size to 10. So when I change that, see now the height are same. When I change the y size to 10, the height are same now. Okay, of both NMOS transistor and the enact. So I'll copy this now. I'll copy it, Control C, select that enact, Control C, and on the left side, Control V, sorry, Control Z to make undo. If anything goes wrong, okay, press Control Z. Okay, press Control Z to make undo. So I will select this, Control C, and on the other side, on the left side, I'll press Control V. So you can see a rectangular here. So place it here. So place the boundary should match. Make use of arrow keys like this, right? So now we have to connect this. Now this NAT has to be connected to the source and the drain. So I will start on the right, from the right hand side. So left click, right click on the destination, on the boundary. Okay, on the boundary of this drain, right click. Similarly, left click, right click on the boundary like this. Now you can move this NAT on the drain. So select this, hold the left key and move it. So when it becomes 3.5, leave. Now it is 3.5, I will leave off. So now see the boundary, it is not matching. I'll make use of arrow keys like this. So now it is match, perfect match. Then similarly, select this, move it inside, hold the left key and move it inside. So when it becomes 3.5, just leave. Now it is 3.5. Okay, so don't, make sure that you don't place the layer in this form like this. See, the boundary is not matching it, right? It is not, there is a mismatch in the boundary. So we can make use of arrow keys. Okay, so when I make use of arrow keys, so it is in this form. Okay, so now this is a perfect match of all the layers. Okay, so now NMOS is ready, and if you want to see, so I will zoom out a little bit. So if you want to see whether it is properly overlapping or no, so what I will do, I will select everything of NMOS transistor. Then I will make use of arrow keys to move it up, move it at the top. So you can see it is perfectly overlapping with PMOS transistor, right? It is perfectly overlapping with PMOS transistor like this. Look at this, right? So when it perfectly overlapping, now then you are well and good to go to the next step. Okay, after this, now both the transistor are perfect. Then save it. Then you can check if any errors are there till this point. Go to tools, DRC, press F5. Okay, then after this, now if you see in the schematic, gate and gate are shorted. This is the drain. Okay, this is the drain. This is my drain. The drain of NMOS and PMOS are shorted. The gate of NMOS and PMOS are shorted. The source of NMOS is connected to ground. The source of PMOS is connected to what? VDD or power supply. Okay, so same thing we have to do it in this case. In case of layout, now we have to connect the gate. The pink color is the gate. So left click here, right click on the destination. Similarly, drain and drain. This is the drain. This is the drain. Okay, like this. Okay. Then the source has to be connected to VDD, and the source of NMOS has to be connected to what? Ground. So to do that, to make the connection, so we will take one more layer from the components. Take P well for NMOS. Take P well for NMOS. Okay, so if you have any confusion which well to take for a particular transistor, Look at this layer. Okay, look at this layer. So this nmos layer and this layer are same, that is we have oblique lines, okay, which are same in fashion, so then it is correct. Okay, then it is correct. Now if you see the, it is not matching, it is not matching the boundary of the nmos transistor. We have changed the width of this p well. Okay, to change the width of this p well, double click on this, then you can change the width of this p well to that is excise 2 of this to, or like suppose now it is 12, or it's not matching it, so we have to make it around 16. If it is there, it's not matching, so we'll see. So make it 20. 20, it is matching, it is not matching 21, so we will change it to 21 and see whether it is changing. Yeah, 21 it is correct, so it will perfect match with 21. The excise, if I keep the excise to 21, it will be perfect, so you can see it is, the boundary is matching here. Okay, and this this p well, the boundary of this p well, it should touch or overlap with NMOS transistor. It should touch or overlap the NMOS transistor like this. So don't give any gap between here, between NMOS and this P valve. Just we have to touch it or just overlap. Okay. Then this is the source now. This is the source terminal. It has to be connected to this P valve, which is the ground now. Okay. So I'll give the name for this P valve. So I will select this P valve. Okay, then press Control E, and give the name for this as GND, small letters GND. Okay, small letters GND. You can see this. So we have given the name as GND. Then this is the source. It has to be connected to this ground. Okay, because we have in the schematic, right, the source here. So this is the source. It has to be connected to ground. So in the layout also, this is the source. Okay, Control 7 to zoom in. So this is the source. Right, left click, right click on the destination. Okay, so you can see it is we are using a metal. Blue is for metal layer, pink is for polysilicon layer. Okay, so I will save it. Again, you can press Control F5 and check. No errors are found. Okay, no errors are there till this point. Similarly, in the components, you take N well and place it above PMOS transistor. Okay, now again see the width of X size is not matching with the PMOS transistor, so we can change, double click on that, that is N well, and change that X size, change the X size to 21 again, so it will match. So it is matching now. Okay, it is matching, so just overlap this N well with, just touch the N well to the PMOS transistor, to the boundary of PMOS transistor, and then now connect this. Now this is the source, it has to be connected to this VDD. So we will give the name for this N well now. So select that, select this N well, select this N well, press Control E and give the name as VDD. Give the name as VDD. That is a power supply. Okay, it has to be connected to VDD, that is small letters VDD. Then we will kind of make the connections now between source and this power supply. Left click, right click on the destination. Okay, left click, right click on the destination. Okay, now save it. Control 7, Control S to save. Go to tools, simulation spice, right? That is, go to tools, DRC, check hierarchical. F5, press F5. So no errors are found. Okay, then now this is done. Then I will zoom out. Okay, so this is the layer we have. Then we have to connect what now? input and output. So to make use of input and output here, okay, so I will take polysilicon 1 pin, small pink square layer here. Look at the cursor, small small square, that is nothing but polysilicon 1 pin. Okay, from the components you select small pink color layer and place it at the input side, that is on the left hand side, like this. Okay, this is a small square. Then make the connection to this vertical pink color layer. We have to make the connection. So left click and right click on the destination, like this. Okay, and whatever, now we have to give the name for this layer, that is the pin, that is polysilicon pin. We have to give the name. So select the tip of this pin, select the tip of this pin, control E, press control E and give the name. Whatever the name we have given in the schematic, it should be same. Okay, it should be same. So click on, select that. So it should so we have given it has in, so I'll give the name has in and click OK. Similarly to the output, what we have to do, we have to select metal 1 pin from the components. So a small blue color, a small square which is in blue color, select that and place it on the output side, that is on the right hand side, like this small square. Then make the connection to this drain, that is the output. Okay, select this, left click, right click on the destination. Okay, now the connection is made between this pin and this drain. So select the tip. Okay, select the tip of this metal pin, press Ctrl E, again the same name what we are given for the output, that is out. Okay, and click small letters out and click OK. Right, so save it, Control S, again you press F5 and check go to tools, DRC, press F5. Okay, F5 means shortcut for DRC, that is. Okay, so we can see in the output pin, that is electric message window, no errors are found at the bottom here. You can see no errors are found. Now the layout is, everything is free of errors. Okay, it is free of errors now, this layout. Now it is time to simulate this with respect to DC code and the transit analysis code. Okay, so same thing again, from the in the explore, go to explorer tab, go to the schematic option, copy this, and just copy this code, select this code, that is Control C, copy it, and go inside the layout, go to this in a layout file. Okay, go to this layout option, select this layout option and paste it here, Control V. Okay, Control V. So see, you can see the text, it is very small. We can increase this text by selecting this, Control I, and you can change the text size. Instead of 1 you can make it 2. Okay, text size you can make it 2 and click apply and OK. Okay, you can see this, a text will appear here. Then save it, then go to tools. We have now it is ready, this layout is ready to ready for simulation. Go to tools, go to simulation, same procedure again, go to tools, simulation spice, write spice tech. Go to tools, simulation spice, write spice tech. Okay, so see, you will get a blank window like this, a white window or black window. Then go to plot settings, visible traces, select Veen, click OK. Right, you'll get this. Similarly, we want the output, go to plot settings, add plot pane. Okay, I will maximize this. Then go to plot settings, visible traces, and now select V out. You can see. So it is perfectly working. The layout is perfectly working with the schematic, right? So whatever the waveforms we are getting for a schematic, the same thing we are getting for the layout. Okay, so this is for transit analysis. Okay, then if you want to do it, if you want to cross verify, or if you want to get the DC analysis waveforms, replace this code, with transient, that is the DC code. Yes, just I'll copy that DC code from here, copy it, and I will paste it here in this window. I will save it. Save it after doing the modification. We have to save it compulsory. Then go to tools, simulation spice, write spice tech. Okay. So again, you look at this window. Then go to plot settings, visible traces, vin. Select first vin. Then to plot the v out, go to plot settings. Select first add plot pane. Then go to plot settings, visible traces. Now you select v out and click OK. If you want to maximize, you can maximize the window like this. You can see, you'll get the waveform. Okay. So this is about the DC analysis waveform or simulation using the layout. Okay. So this is about experiment number 1, that is CMOS inverter schematic with DC and transit analysis, and also we have seen the how to draw the layout and do the DRC, and we got the waveforms for DC analysis and transit analysis. Okay, so we have to verify three important properties. One is with respect to what? DRC, that is a design rule check. The third one is what? ERC. ERC means electrical rule check. Okay, so in the exam they will write the question, verify the following parameters, that is DRC, that is design rule check. Whatever you are pressing F5, that is nothing but design rule check. Then the second one is what? ERC. ERC for electrical rule check. Okay, so in the tools, go to ERC and select check files. Select check files. You should you can see in the electric message window, you should get no well errors found. No well errors found. You should get this message. Okay. If you're not getting this message, then there is a problem in the layout or in the settings. Okay. Go to tools, ERC, and select check wells. No well errors are found. Then the third one is NCC, but we don't use NCC term, we use LVS. We use LVS, that is layout versus schematic. That is layout versus schematic. So go to tools, NCC, select NCC, and from NCC select the first option, schematic and layout views of the cell in current window. Select the first option. Okay. Then you should see a summary of all cells. Export match, topologies match, and sizes are not checked. Here you can see the message sizes are not checked. Means what? So we have to do some settings. Okay, we have to do some settings. So to do the settings, go to file, and in the file select preferences. Okay, select preferences, and in the preferences, go to tools, go to tools, in tools go to NCC. Okay, go to tools, select NCC. In NCC you can see there's one option, check transistor sizes. Check transistor sizes, make sure that it should be check. This option should be check mark. Okay, it has to be selected. Okay, if you see the message like sizes not checked, means what? This option has been disabled. This option has to be is been disabled. We have to enable that. Okay, so we have to go to file. Where we have to go? We have to go to file, preferences. In preferences, we have to go to tools. In tools, we have to go to NCC. In NCC, we have to see that check transistor size is enabled. So if it is not enabled, make it enable or make it check mark like this, and click apply and click OK. Okay. Save it. Now tool verified, save first, save it. Then go to tools. Now you select NCC and select the first option, that is schematic and layout views of cell in current window. You can see summary of all cells, export match, topologies match, and sizes match. So all the three should be match. All the three should be match. Export match, topologies match, and sizes match. Okay, so these are the three parameters we have to verify in the layout. First one is DRC. So that is nothing but F5. Whatever you press F5, so that is nothing but what? DRC. Next one is ERC, electrical rule check. And third one is what? NCC or LVS. LVS stands for layout versus schematic. And NCC will stand for what? Network consistency check. Network consistency check. Okay. So sometimes they will, because in case in the question in the exam, they will write LVS, not NCC. Okay. NCC with respect to tool, but LVS is what? Layout versus schematic. Okay, we have to compare whether layout and schematic are same or not. Okay, so that is about LPS, right? Then, so if we do any mistakes, suppose for example, okay, suppose for example, here instead of out, if I write instead of out, if I write here, suppose for this, instead of out, first I've deleted that. I will write capital O, like capital out. Okay, suppose if I write capital out. Okay, so see this. Now I'm writing here in the layout has out, but in the schematic, what have written small letter out, small letters out. Alpha, that is small letter that is out. But in the layout, what I have written capital out. In the layout, I what I have written capital out. Right. So there is a mismatch. So if you do the LBS, I will save it. Now if I do NCC, and if I select schematic versus layout, you can see we'll get a window, we'll get error like this. We'll get a window like this. You can see at the bottom in the electric messages, export mismatch, topologies match, and sizes match. Export mismatch means what? Whatever the name we have given the export name, that is out, that is capital out, and in the schematic it is small out. There is a mismatch. Okay, so that is how we can identify where exactly the error is there. Okay, so make sure that whatever the name you have give in the schematic, the same name we have to give in the layout. Okay, so I'll rectify that error. So I'll delete this. I'll give the name for this as small out, small letter out. That is out here. I will save it. Then I will verify that again. NCC schematic. So now you can see export match, topologies match, and sizes match. Okay, so this is what about the layout. Okay, so this will complete the experiment number one, that is CMOS inverter. Okay, so we have drawn the schematic. Okay, we have drawn the schematic. We have simulated DC analysis and transit analysis for schematic part. Then in the layout part, we have draw the layout, and we have to verify whether we are getting the same output in the layout or no with respect to the schematic. Okay, that is check whether the waveforms are correct or no. That is DC analysis and transient analysis. So after that, you verify the three parameters, that is DRC, ERC, and LVS. Okay, DRC, ERC, and LVS. Okay, so this is about lab number one, that is experiment number one, CMOS inverter. So we'll stop it here, and in the next video we'll see, that is lab 2, that is experiment number 2, CMOS, common source amplifier. Okay, that is schematic as well as layout. Okay, thank you everyone. We'll stop it here.